From the youngest of ages, as kids, we learn to count. And there's a certain excitement for many children, I definitely felt it myself, in the magic of learning about bigger and bigger numbers. I can't remember the first time I was told about 20 and the world beyond it, but I'm sure it blew my geeky little 3 or 4-year-old mind. Then we learned about 100, 1,000, then words like a million and a billion that for many people remain fairly meaningless for most of their lives. So today I thought we'd take a quick tour of some big numbers, like really big numbers. I should point out from the outset, the counting numbers are infinite, so no matter how large these numbers we're about to meet are, they're not even really small compared to the infinity of all counting numbers. Even in their immensity, they are vanishingly minor, but I don't want to rain on their parade. So let's meet some big numbers. Now, before we dive in, there's one thing I need to explain to you. When it comes to writing numbers with lots and lots of digits, not like the number 57 or 294 or even 32,109, but long numbers like, let's say 123,546,768,209. Mathematicians like to save a bit of time. We like to use a shorthand. And this is how it works. If you recall powers from mathematics at school, remember when numbers got all weird and began floating up in the air? Do you remember that? 5 with that little 2 up there is just another way of writing 5 times 5. We call it 5 squared or 5 to the power of 2. It's not magic, it's not a new sort of special number or a new rule in mathematics. It's just a shorthand, another way of writing something that's no more complicated as a concept than multiplying 5 by 5, which we all know is 25. So in the case of 5 to the power of 2, the shorthand is barely any quicker than writing just 5 times 5. But trust me, you'll soon see how this notation is a game changer when it comes to writing large numbers. Let's take a 7 with a 3 floating above, which we pronounce as 7 to the power of 3 or 7 cubed. It's 7 times 7 times 7. There's 3 sevens there, which in case you're wondering is 343. So already you should be able to see that 7 cubed is quicker to write than 7 times 7 times 7. So 10 to the power of 6 or 10 to the 6 would be 10 times 10 times 10 times 10 times 10 times 10, which is 1,000,000 or 1 million. And the important thing to note here is that the 10 to the 6 has exactly 6 zeros after the 1. That's no coincidence if you think about it. Multiply 10 by 10 a few times and you'll see how you add exactly 1 0 each time you go from 10 to 100 to 1,000 and so on. This is the basis of the shorthand we use to abbreviate massive numbers. We call it index notation. 1,000 is 10 to the 3. 10,000 is 10 to the 4. 100,000 is 10 to the 5, as we've already seen. 1 million is 10 to the 6. And in each case, the number in the power, which we sometimes call the exponent, the number that just floats mysteriously in the air, matches exactly the number of zeros after the 1. So given a big number like this, you should realise we just count the number of zeros after the 1. And here they are, nicely grouped in 3s. There's 4 lots of 3, that's 12, plus 1 more. There's 13 zeros after the 1. So this number, which just happens to be 10 trillion, can be written in index notation as 10 to the 13. Now, when a number's not equal to an exact power of 10, we can still use index notation to shorten what we have to write out. If you look at the number 7 billion, you can count 9 zeros after the 7. We know that 1 billion, 1, comma, 000, 000, 000 is 10 to the 9. Again, the 9 zeros after the 1 match the power of 9. So you should be able to see that 7 billion is equal to 7 lots of 1 billion, or equals 7 times 10 to the 9. And even if numbers aren't as beautifully exact as 7 billion, index notation can still help us out. Let's take a simple example first and then we'll work our way up. 100 is 10 squared. So 300 is 3 times 10 squared. So what's 3.5 times 10 squared? Well, it's 3.5 times 100, so just 350. So the 5 immediately after the decimal place, or the 5 that was next to the 3, stays next to the 3 when we expand out the number from its index notation into its original form. Let's take an example like 3.82 times 10 to the 5. That's 3.82 times 100,000. Note again, the 5 zeros after the 1 match the 5 in the power. So that's 3.82 times 10 to the 5 is 382,000. And again, the 8 and the 2 after the 3 stay next to the 3 from index form into the final answer. Do you follow? If not, roll the video back and take another go, because it's important you understand what this notation means.
Hate to interrupt. Would you prefer uninterrupted indulgence? Head to findqualia.com to access the entire series by comedian, broadcaster, and mathematician Adam Spencer, completely ad-free.
Now, at the time that I was recording this, the world's population was, from a clock I looked up online, 7,778,730,947. Though even as I typed out that number, the population raced on. Anyway, it will do for our purposes. This is not an exact billion, but following the logic above, perhaps with a pen and paper, you should be able to see it's exactly 7.778730,947 times 10 to the 9. You can see this because in our original number, there are 9 digits after the 7. And when we write the number in index notation, there is 9 in the power. And the digits that follow the 7 are exactly the same in both the original number and the index form. Play with this and see that example works. Work through that example a few times if you don't quite get it. See why those two numbers are exactly the same. Now, this new notation might be an exact match for the original number, but it hasn't helped us save any time, has it? In fact, writing this number in this way in index notation is more laborious than writing the original number. So what we tend to do is approximate really large numbers by trimming down the number in front of the 10 to the power of, to give us a near enough is good enough version of the large number we're describing. For example, if you're trying to capture the world's population for any effective discussion on food security, global warming, disease prevention, you probably don't need to know the number exact to every single person on Earth. To be honest, to the nearest million would probably do you. So a number like the one we had, which you'll remember was 7,778,730,947, which has already gone up in the time we've been chatting by a few hundred, could be written as, say, 7.79 times 10 to the 9. That's 7,779,000,000. And that would do for all intents and purposes. Okay? So now that you understand index notation, let's go meet some big numbers. Kicking off our mega number hit parade, we've already met her. She's a beauty. Let's have a big round of applause for the population of the world, give or take 7.8 times 10 to the 9. The US national debt in dollars is 2.5 times 10 to the 13, or $25 trillion. The number of meters that light travels in a year is 9.461 times 10 to the 15. The number of ways you can arrange a Rubik's Cube is roughly 4.3 times 10 to the 19. That's 43 million millions of millions. I love Rubik's Cubes. Avogadro's number, a number used in chemistry to compare the mass of different compounds, begins with a 6 and is 24 digits long. The order of the geometric construction, the monster group, which we met in our chapter on symmetry and groups, was roughly 8 times 10 to the 53. One of the most famous mathematicians of the ancient world, Archimedes, estimated in his famous work, The Sand Reckoner, that the number of grains of sand that the universe could hold would be, give or take, 8 times 10 to the 63. The number of shufflings of a standard deck of cards is a mind-blowing 8.06 times 10 to the 67. There's another video in this series that puts this number in some form of perspective and gives you a party trick that's well worth learning. For our next massive number today, I need to explain that our best estimate of the number of fundamental particles in the entire observable universe is not an exact number. And hey, if you think about it, it's a pretty deep question, so it shouldn't surprise you we don't have a final answer. But if you're trying to count up all the bits of the most elementary pieces of stuff in the section of the universe we can see, you're looking at a number in the vicinity of 10 to the 85. That's 1 followed by 85 zeros. All this and we haven't even got to Google yet, the word invented by 9-year-old Milton Sirota when his uncle Edward Kasner asked for a name to describe the number 1 followed by 100 zeros. That's right, a Google is 10 to the 100. And yes, that's how you spell Google, G-O-O-G-O-L. And yes, the search engine is a misspelling of that word. Some kids even like to blow each other's minds by talking about a googolplex, which is 1 followed by a googol zeros, or 10 to the power of 10 to the power of 100. This fantastically large number, it's bigger than anything you'd ever need to count any amount of anything in the real world. Don't forget that an 85-digit number is pretty much all you'd need to estimate the number of bits of basic stuff in the entire universe. So a googol alone would estimate the number of bits of fundamental stuff in about 10 to the 15 universes. Yes, you would need 1 quadrillion, that's 1,000 trillion or 1,000,000 billion, whichever way you look at it, you've lost me already. But you'd need that many of our universe before you have a googol fundamental particles. Well, a googolplex is 1 followed by a googol zeros. Now, if that blows your mind, and that's quite reasonable, you might need a good lie down, because in our next video, we're going to meet an absolute monster of a number that puts even googolplex in the shade.